All right, so let's start the evaluation course. Hello, my name is Truman Vu, and I'm a new instructor here at iGo Learning. A little bit about myself. I'm currently a third year at UC Santa Cruz, and I'm studying computer science. In today's lesson, there will be certain things that I mention that I will assume you have already learned in the previous courses, 1006 and below. So that's data structures and algorithms with Java, PyCharm, Python, etc. However, do feel free to privately ask me any questions regarding any terminology I use, or really just anything that you don't quite understand. And yeah, feel free to raise your hand if you have a question regarding, any time during the presentation. So yeah, let's begin. So today I'll be teaching you binary search. So what is binary search and why should I care as a coder? Is probably what you're wondering. But really, why should I care as maybe even a programmer, developer, just anything that has to do with problem solving? Although it's just one algorithm, it is one of the foundational algorithms that you'll probably learn as a someone studying computer science. And as you dive deeper, it'll stem from that. So what is binary search? Binary search, as defined, is a searching algorithm used in a sorted array by repeatedly dividing the search interval in half. Now that's a literal definition, and I'll show you even an example later. But to summarize, it's an algorithm that we use to, and every time we call on it, it shortens the interval that we search through. And I'll show you later in the next slide an example, but in reality, this is what it should be doing. Like this is the entire goal. And the entire goal of binary search, if anything, the main one is that the idea of binary search is to use the information that the array is sorted and reduce the time complexity to O log n. So this is one of the terms that I would assume you would know, big O, which stands for time complexity, and log n standing for the amount of elements you're going through, log standing for logarithmic. So yeah, the next slide I'll show you is an example of binary search being implemented. So in this example, you have a total of 10 elements, and remember, it's a sorted array. And the element we're trying to look for is 23. Now, if we ran binary search, we would have to first start off with a search interval. The very first search interval that we start off with is from 0, as seen here, to height to the total length of the array, which is 9. Or total, the length is 10, correct, but the highest index is 9. And the middle is the lowest plus the highest divided by 2. And it's 0 plus 9 divided by 2, which is 4.5. A lot of you would probably think, right? But we don't really have a 4.5 index. We only have integers as index. So to, go against that, after we divide, we have two choices. We can either floor it, which is we round down, or we seal, which is we round up. I say that no matter what you do, as long as you stay consistent throughout the entire implementation of your algorithm, then it shouldn't matter. So in this example, we've rounded down. So the middle index or the middle pointer is 4. So the index 4 of the array, the element in index 4 of the array is 16. Now we do our conditions. So is 16 greater than 23, less than 23? Is it 23? As you can see, 16 is less than 23. And in that case, when the middle element is less than the key that we're looking for, then we shift the lowest number of the search interval, which is 0, and we move it up to the middle or past the middle, right? Because we know it's less than 23, so we can just skip it, right? So there's no point in keeping it there. So we move it to 5. So as you can see here, it goes from 0, the search interval goes from 0 to 9 to 5 to 9. And we repeat the process again. So 5 plus 9 is 14. 14 divided by 2 is 7. And we look at the element at index 7, and it's 56. 56 is greater than 23. So in this case, we bring the highest index of the search interval, which is the end of the search interval, down. And again, skip over the 7th, right? Because we already know it's not 23, it's going to be higher than 23. So why should we cover it? So it goes from 5 to 9, index is 5 to 9, to index 5 to 6. And then we do it again. 5 plus 6 is 11. 11 divided by 2 is 5.5, but we're flooring it, so it's 5. Now, in this case, we check the number at index 5, which is 23. It's not less than 23, it's not greater than 23, it's exactly 23. And with our algorithm, it should return at the index that it's found. So in this case, index 5. So that's my example of binary search. Of course, we'll go into, if you have any questions, feel free to ask. But as you can see, it's like the definition from the last slide. It's a searching algorithm used in a sorted array by repeatedly dividing the search interval in half. In this case, we've divided it 3 times in half, or really just 2 times. You go from 0 to 9 to 5 to 9, and then to 5 to 6. So it keeps dividing it in half until it eventually finds, or doesn't find, the element you're searching for. So why should you care? I think this is a really important thing that we should talk about. Why should we care about certain things that we're learning, right? I think that's a great question to ask, because a lot of times, me personally, when I was younger, when I was learning more or less certain algorithms, I was wondering, when would I ever apply this, or when should I ever, use this? Like, makes no sense. But if you think about what it's used for, and then you try to expand on it, then I think you'd find a reason. But here's my reason, at least. So again, when I said in the beginning that time complexity would be one of the main parts of this algorithm, I wasn't kidding. It is. The time complexity of this algorithm should always be, best case, O, big O, log n. So which means that the operation is proportional to the logarithm of its input size, as I said earlier. So let's go back to our example. In the last example, there were 10 inputs, right? And our key was 23. Now, if we had decided to look from the very start and count each element and see if it was our key, that would take us, what, 6 operations? We start at 2, 1, 2, 3, 4, 5, 6. Let me find 23. So that's 6 operations. Really simple, right? It's 6. It's just 6. But with our binary search algorithm, we made it from 6 operations to just 3 operations. 1, 2, 3. Simple as that. So the reason why I'm saying this is that when we think of the bigger usage, right? Now, let's say you were a big company, you need to find a person, in your bajillion, user data set, right? Of course, it's all sorted out, but there's still a billion of them. If you had counted from the very start to where the user is at, it would take forever. You'd get lucky if the user was at the very front. But imagine if the user was at the very end. That would take you a billion times operations, right? But with the binary search, it would take you the logarithm of a billion, which is way faster than a billion. So one of the things I want to, highlight is that when we code, when we make algorithms, when we make anything, we always need to consider the worst case in these scenarios and try to search for a specific element inside a sorted list of elements. So with this, binary search would be ideal for that. So the reason why I think that binary search would be so great is that it has efficiency, it's a core algorithm. Again, I say core algorithm. If you think this is hard, or if you think this is complex, wait until you learn other algorithms. We also use it in interview preparation, real world application, as well as just starting to understand complexity, as I mentioned. So yeah, this is one of the first algorithms you'll learn. And I think it's best that you try your best to learn this, remember it like it's the back of your hand. If you're able to master this, you'll have a better start when learning other algorithms. All right, so let's start with how you can make it. This isn't something that only like the, top 1% can learn. This is something that anyone can learn and implement even. So there are 2 ways to implement the binary search. There's the iterative, and the iterative is basically an approach that uses loops and repeated steps to solve a problem. It uses a set of instructions that are executed repeatedly until a certain condition is met or the problem is solved. So, typically, iterative, functions, algorithms, whatnot, include for loops, while loops, and do while loops. And I'll show you examples of it after the slide, but the second way to implement a binary search is a recursive. Now, before we continue, um, you could even simplify it by saying iterative is just non-recursive. Simple as that. But what a recursive approach to this problem would be is it involves breaking down a problem into smaller and similar subproblems and solving them by calling the same function or method. It's kind of like what, sorry, excuse me. I need a cough real sec. So it's kind of like binary search, right? We split it, we broke it down into a problem to smaller, similar subproblems, right? It's kind of like it, right? But remember, recursive isn't limited to only binary search. We can use it for other algorithms, other problems. We even use it daily, even. But I'll explain it later. In summary, I think either way you use it should be great, but there are obviously pros and cons, both of them. And that is something that I'll talk about later. So let's start with iterative, non-recursive. So here I've provided some pseudocode about how to implement it with an iterative approach, right? So we define our function with binary search. There are two inputs, two parameters. There's the array that we're looking through, and then there's the key that we're looking for inside the array. Now, at the very start, there are two variables that we want to set right off the bat. There's the low, should be 0, and there's the high, which is equal to the length of the array minus 1. These two variables represent the lowest index and the highest index of the array. So this is where we run our while loop. While low is less than or equal to high, we create another variable called mid, which is the middle index, which is equal to low plus high divided by 2. And again, this is where you choose to either floor down or ceil up, which is, in translation, round down or round up. Let's say so now, after we've created our mid variable, we have our conditions. If key is equal to element at index mid, so if the key that we're looking at is equal to the element at the index mid of the array, then we just return the mid. We found it. However, that's very hopeful. Unless you've known that it's the middle of the index, then you'd probably have to run it again. And this is where the other conditions run. Else, if key is less than the element at index mid, the key that we're looking for is less than the element at the middle. That means the element at the middle is greater than the key, right? Then we bring down our high variable down to middle. We set it equal to middle minus 1. Remember, we're skipping over middle, or the element at middle, because we know that element at middle is already greater than the key we're looking for. So there's no point to keep it in our next search. And then obviously else. Else would be if key is greater than element index middle, right? Index mid, sorry. And in that case, we would bring low is now equal to mid plus 1, right? Remember, these variables that we create are just representing indexes. And then to access the elements in the array, we would do how, I don't want to say it because I would be showing you the code, but I just want to remind you that these variables should just represent the indexes. And we do that until two things. One, we find it, right? If key is equal to element index mid, return mid. So that's our break statement of the while loop. Or there's a second break statement where, remember, our while loop is while low is less than or equal to high. There will come a time where your low may or may not be greater than high. And if that's the case, it breaks. You just have to make sure that it does, eventually do that. So yeah, If it breaks and it doesn't find your array or your key, my bad, in the array, then you return -1. So yeah, that's the iterative approach to a binary search. And then next would be recursive. Recursive. Oh man, recursive. So recursive is a bit different. It's different with how you initiate things, right? In this case, you don't create a single variable. However, you have two more inputs. You still have the array that you're searching through. However, now you have the low index and the high index already placed in the parameters. There's still obviously your key. Sorry, excuse me. All right, so to start off with our binary search, we start off with our if low is greater than high. If low is greater than high, that means that our low index has passed our high index, and now it's kind of in a weird spot. So if that's the case, then return -1. And if it isn't the case, if low is less than or equal to high, then do the rest. And the rest is the same-ish, right? You still have one variable, mid, where you set it equal to low plus high divided by 2, round down or round up. If key is equal to element at index mid, turn mid, we still have these conditions. All the conditions are same, but what we do after the conditions are still a bit different. So else if key is less than element at index mid, return binary search of your parameters. Now, I've left these blank because I don't want to give any hints, but if you try to look at it from what you've done at iterative and take it over to recursive, then it should give you kind of an idea of what you should be inputting into your parameters. However, by returning binary search, right, the function, we would call it again. So now we've called it again and again and again and again. The idea is you call it again and again and again until it finally either returns mid, which is if key is equal to element at index mid, or returns -1. So yeah, those are the two approaches to binary search. And I just want to talk about just iterative versus recursive. It's something that isn't just, again, like I said earlier, limited to binary search. So the advantages of iterative, space complexity, non-recursive binary search typically has a better space complexity, sorry, compared to its recursive counterpart. Recursion, it often requires additional memory to store the call stack. If you know what that term is, good for you. While non-recursive only uses constant amount of space for variables. Also, there's stack overflows, where, iterative would reduce the risk of, having stack overflow errors, because realistically, we should be using this for larger data sets. So the larger it is, the more troublesome it may be. But iterative just takes care of all that, makes it just safer when you're searching through large arrays. Better performance in terms of physical performance, right? It's not taking recursive function calls on itself. It's more efficient in terms of execution speed, memory usage, and like I said earlier, especially for large data sets. So yeah, and it's iterative, right? It's one of the first things that we've learned. We didn't learn recursion before iterative, right? We learned how to do for loops, while loops, and do while loops before we learned how to call a function on itself. So yeah, that's some of the advantages of iterative. There are definitely cons, but these are just the advantages. And now the advantages of recursive. It's simple and there's clarity, right? There's no while loops. There's no having to take care of, any of that. It's just calling itself on its own, having its condition to return at the very top. And it's very straightforward. And if you understand it, then it's very simple. It's also very concise, as we saw earlier. It's not within a while loop. It's just 3 statements and executes the code, right? It's also used for more abstract data structures. If you've learned abstract data structures, you've probably learned about, let's say, graphs, you know, binary, not binary, binary search trees, even red and black trees, all types of stuff like that. So, it's really used for also trees or graphs recursion because trees and graphs also use the same recursive principle. So it's also more versatile in those scenarios. And readability, which also comes with the simple and clarity. But to just summarize and really not to stay back on topic, it's just that recursion is more for simplicity, elegance, readability, whereas iterative is more for reduced space complexity, better performance, and safety when dealing with large data sets. So whatever you choose when you're trying to implement your binary search or just any algorithm or function in the future, just think about which one would you rather do? Like which one's better in this situation? It's always about what's best for the scenario. And also really just what you want to do, right? All right. So before I continue, are there any questions? Sorry about that. Are there any questions about binary search? All right. I'm going to move on to the next task, but I just want to remind you if there are any questions, I'll drop the link to the Google Slides in the chat room so you can look at it. And you can always privately message me if there are any questions. My job is to make sure that you understand binary search. All right. So moving on. So again, my job is to make sure you understand binary search. So what better way than to have you do something with binary search? So you have a task today, and here's the prompt. People know that the best way to play high-low on a given interval is to guess the half of the interval at any given point. For example, if you pick 50 out of numbers 1 to 100, right? Pick 50, which is the middle, and the other person says higher, then you should pick 75 because it's the between 50 and 100, right? And so on and so forth until you find the number that's in their range. But a programmer might be too lazy to do that. Some programmer, totally not like me. So they decided to implement an algorithm for finding a number in a given array efficiently. Sadly, they're not too good at programming. They know it's possible and they need your help. So, in summary, this is your task. Implement a binary search algorithm to find a number n taken from the input, console input. So, you'll have to ask them what number it is they're trying to find in a given array of size t, also asking them. So, you have to also ask them, how big is this array? And at the very end of it, display the number's position in the array. The number isn't in the array, display that it isn't in the array as well as the -1 or returning. And yes, I will be putting this on the Google Slides and screen share prompt right here. I'll leave this on so that everyone can see it while they're working on their binary search. But if you want the pseudocode, you'll have to click on the slides as well that I'll drop in the chat room. But yes, that is your prompt for today. And yeah, if you have any questions regarding binary search or any of the terminology I went over, or really anything regarding today's course, or really just anything you want to ask me, because I'm one of the new instructors, feel free to private message me. And that should be it for today. And yeah, I think that's it for my evaluation video. Thank you for listening. I hope to be able to teach more. I was really excited about teaching the C++ course. So I also have a lot of, I say credentials, but it's more so just GitHub projects in C++ if you really need that. But yeah, I think that should be it. And I'm willing to always teach more courses. I think it would be great. Thank you for watching and have a nice day. How do I pause this thing?